Hi, everybody. Hope you're doing okay. We're at an exciting time in Calculus 1. Um, we've been doing a lot of derivatives lately, and now we're going to the flip side. We're going to be doing antiderivatives and getting into integrals. Um, if you haven't already, go ahead and pause my video here. I would like you to watch the first 9.5 minutes of this video from Three Blue, One Browns, Essence of Calculus. It's the eighth video in that. I put it on our playlist. So the first 9.5 minutes is going to be introducing the idea of integration as a way of accumulating values over an interval. Um, so that's good. And the rest of that video is about the fundamental theorem of calculus, so we don't need to watch that yet. We'll get there. Um, so go ahead and watch that, and then we'll start back in. Okay, so now that you've watched that video, you've got an idea of what to expect with integration. Um, I want to make it clear that there's kind of three separate things that we might be expecting when we do integration of some kind of thing. So what we're talking about here initially are what are called antiderivatives. And the idea is we're just kind of undoing the process of taking a derivative, and we're trying to think of what parent function would have given us the derivative. And we've noticed that we've done this a couple times so far. Whenever we try to think of this parent function, f of x, uh, this one, um, we're either like reversing the power rule or maybe cosine turns back into sine, something like that. But uh, there's also this extra thing that comes out of here, a plus c. This is just some constant. And it's a constant that we could have lost um, after doing the derivative. So if we took the derivative of this big f function and we had a plus c, when we take the derivative, we would just get, f prime, or, what we're calling this little f function. Um, and so, yeah, this c can go away when we take a derivative. So we have to add it back when we take an antiderivative. And really what this gives us is I would like to call this, it's a family of functions. Because, we can change that constant and still have a general antiderivative. Um, so there are many functions just, depending on whatever the value of c is. It could be 3, it could be 100, it could be 0, anything. But yeah, this gives us more than just one function to narrow in on. There's something that we're going to learn about fairly soon, probably in 5.3 or 5.4. Um, an area function is something that if we had a function f of t, um, I don't know, maybe I do a little bit of a drawing here. There's not much room. Let's go ahead and do a little drawing. Yikes. F of t. Um, we could make an area function where we start at some fixed value. Maybe we're starting off at the x value, x equals 1. And then what we're doing is we're trying to calculate area um, as a function of the second boundary on our interval or on our integral. So this x value is kind of a slidable thing, is maybe the way that you would want to think about it. But the area underneath this curve, we could call big f of x. And this is a cool consequence of the fundamental theorem of calculus that we will talk about soon, but not right now. So I guess the main thing that I want to say is that, as we're talking about integrals, um, here, when we don't put any specified boundaries on the integral, we could just get a family of functions, and we do this plus c thing. Here, where we've got one constant boundary and one variable boundary, we kind of set up this thing that's like an area function where one of the boundaries stays fixed, the other one slidable, and we get this new function that whenever we put in x, we get the area underneath the curve up until x, kind of a thing. So this is just one function. And then finally, the definite integral, which we're going to actually learn about very soon. The thing that you end up getting out of a definite integral is just a number. This is where both parts, both boundaries on the input, the integral are fixed. And so we're just finding a number, which is the area underneath that curve to the x-axis, kind of a thing. So I wanted to let you know that these three different things are all coming up. They're all related. So example one here, let's go ahead and focus in on finding some antiderivatives. We're just practicing finding that parent function. We're doing this part. It's an antiderivative, sometimes called an indefinite integral, if we were to utilize this notation. But this is the part where we're going to get plus c's. So if little f of x is 3x squared, we could make a big f of x by taking the indefinite integral. Maybe, if we wanted to get used to that notation, we could go integral f of x dx equals. That part's not so important right now. But yeah, big F of x would be undoing the power rule on this. So whenever we're undoing the power rule, we're actually going to add 1 to the exponent first, and then we're going to divide by that exponent. So the idea would be add 1 to the exponent and give us x cubed, but we're also going to divide by that exponent, so it just becomes, x cubed. So yeah, the 3x squared becomes 3x cubed first, and then you would divide by 3, and you get just a plain old x cubed. And that makes sense. On both of these occasions, yeah, it would be most correct to put a plus c there because there could have been a constant that was lost in the process of taking a derivative. Next one, we've got sine. We're undoing this process. And so thinking of the antiderivative means, okay, we get big G, and that would be negative cosine of x, because whenever you take the derivative of negative cosine, you get sine. And so we would add on a c there, and that's a good general antiderivative. One more example, if we get a big h of x, 1 over x is the result of taking the derivative of the natural log of x. So going back to the natural log, I'll write things like this. Notice that I'm putting absolute value signs around that x. Natural log has that property that we only want to put positive values into that. So depending on the domain of this function, like h of x here, like little h, you could put positive and negative values in for h, but we wouldn't want to put negative values into the natural log. So making this an absolute value means that we're going to be able to put negative x's in there as well. Maybe we'll take a look at a graph real quick after I do this. So let's do the second part. Reversing the power rule means adding 1 to the exponent on x. So right now the exponent on x is 0. And so now we've got x to the first power when we reverse the power rule. And then I'll go ahead and throw a plus c on that. You know what? Let's, we'll take a little break. We'll go to GeoGebra. And I wasn't necessarily planning on doing this, but, since this is the first time that we're taking the antiderivative of a 1 over x, it's probably a good idea to show you why this should be a natural log. Okay, there we go, 1 over x plus 5. Yuck. So, all right, we zoom out a little bit. Here's our original function, that 1 over x plus 5. Cool. What we're doing is we're treating this as the derivative of some unknown function. Let's go ahead and make a slider c real quick. So that's something that we can utilize when we make capital H. But what we said was, all right, natural log, oh geez, natural log of, oh, sorry, the absolute value of x plus 5x plus c. Woo! Okay, so I put that absolute value of x on there to show you that we need to be able to put in values like -4 into this function. And yeah, if we didn't have those absolute values, let's see what happens if I just throw in, natural log of x plus 5x plus c, whatever. Um, this one has a c value of 0. You can see that this is only defined for positive values of x. And, theoretically, this part over here should have a derivative as well. And, taking the absolute value of x is completely fine for, finding this antiderivative. So, yeah, if we don't put those absolute value signs, we only get half of what we need. But yeah, the cool thing about C is that we should be able to raise this up and down. And since even if we raise this up and down, the slopes on this blue function aren't changing, it means that, this derivative, little h is the derivative of big H. It's there. Actually, let's try this real quick. Let's make another function, uh, big H, and let's go prime of x. E. Um, cool. Yeah, look at that. It ends up being the same thing as our original function h here. And so we took the derivative of big H and it ends up being little h. And the cool thing is even when we switch this, there's no c in this one anymore. So it doesn't change at all. We're fine. Okay, cool, cool, cool. Let's go back to this and keep moving on. All right, so this next table I wanted us to look at is labeled general antiderivatives. And these are just some thoughts that we might have for reversing the thinking that we're used to and doing antiderivatives instead of derivatives. Um, all of these hopefully will make sense, though, in time. So if we start off with a function that is some constant k times f of x, um, this k can just chill out front. It's still a scale factor. Just like if you were going to take the derivative of this, k could just come along for the ride as you take the derivative. The c would go away, kind of a thing. Constants can ride out in front, and that's totally cool. Taking the antiderivative of the sum of two functions is still just the sum of their antiderivatives. So we're going to be able to take antiderivatives term by term. That's totally fine. This one is the power rule. Oh, geez, that's not how you spell power. Power rule. But it's just the opposite. Um, in this one, you add 1 to exponent, and then you divide by the exponent. And so that'll just be a new rhythm that we get into. Sure, 1 over x becomes the natural log of the absolute value of x. E to the kx becomes e to the kx here with a 1 over k. There's an explanation over here, but the idea is if we have a kx up in the exponent of e to the x, if we were taking the derivative, there would be a chain rule going on, right? Because we've got a littler function inside of a bigger function. And normally when we take the chain rule, we end up taking the derivative of the big function and then multiplying by the derivative of the littler one. And so when we're going back in time and we're taking an antiderivative, instead of multiplying by that k, we end up dividing by that k. So that's something that we're going to get used to as well. Sometimes we're going to be able to just undo the chain rule, and instead of multiplying like we do in the chain rule, we're going to divide as we go backwards in time. And same here. We end up dividing by 1 times k over the natural log of a. That is, for the same reason as this one. Here are some more functions. I highlighted these ones because, the basic functions are the ones that I'm most interested in. So these 6, which are the sine, cosine, secant, cosecant, tangent, cotangent, those ones are probably the most important. These inverse trig functions are cool. I mean, if you get an integral where you've got this on the inside, knowing that it will go back to the arc sine is a cool thing to know. Similarly with this, especially this one, where it's 1 over 1 plus x squared or something, knowing that this goes back to an arctangent is cool, but I'm gonna try not to, throw these at you. It's a lot to memorize already. So I'm not gonna throw these out you without a warning, or at least allowing you to use resources like looking up this formula kind of a thing. If I had to put it on a test, I'd be happy to give you a formula sheet with this on it. But yeah, all of these are just going backwards in time, knowing that we've got this factor of 1 over k. That's because we're reversing the chain rule. And, since the derivative of kx is k, we're dividing by that as we do the antiderivative. Cool. All right, on to example 3. These functions are a little bit more complicated, but they're not too bad. Again, going term by term is the way to go. So let's make big F of x. Yeah, realizing that this is x to the negative 1/2 is probably a good, oh, shoot. Let me go ahead and just label this as f of x so that we can get things into a nice form before we actually take the derivative. So yeah, not taking a derivative yet, just setting ourselves up for success. I think oftentimes writing it as a rational exponent rather than having the square root is fine, but if you like the square root better, more power to you. So we're doing a power rule here in reverse. We're going to add 1 to the exponent, so x to the 1/2 power, and then we're going to divide by that exponent. And as we do this, it's fine to go through and say divided by 1/2, but most of the time it's going to save you time and effort. Instead of dividing by a fraction to multiply by its reciprocal. So I'll go ahead and write this down, but I'm also going to write this down because this is what I would normally just skip to. That's 2 times x to the 1/2, or 2 times the square root of x. Yeah, normally multiplying by the reciprocal is the way to go rather than dividing by a fraction. Anyways, if we go backwards in time on cosecant squared, particularly negative cosecant squared, that would just be a regular cotangent 5x, but realizing that we need to undo the chain rule and remember to divide by the derivative of the inside, that's where a 1/5 would come into play. And then, yeah, to finish this out, putting a constant at the end would be a good idea. So, yeah, this would probably be my final answer. And if you wanted to write that as a square root, it's fine. No big deal. Okay. Next one. Actually, I'm going to do the same thing. We're going to keep this as little g and try to reduce this so that we're not having to like undo a quotient rule thing here. Let's go ahead and just divide through so that we've got 7/2, and then we would have x to the 1/3 power when we divide x to the 4/3 by x. Then we would have plus 3 halves, and then we would have x to the negative 1/2 power when we divide x to the 1/2 by x to the 1. We're subtracting exponents, right? And then 2 to the x can just chill. All right, so that's the function. I think we're ready to take antiderivative now. So we go big G, and yeah, we're going to add 1 to the exponent. And then divide by that exponent. But remember, I said dividing by 4/3 is the same as multiplying by 3/4. So I would go like this if I were working it. Which I guess I am right now. Here we add 1 to the exponent, and then we divide by 1/2 or multiply by 2. So multiply by 2 over 1. That's good. For this last one, we've got 2 to the x. This is one that if we were going to take the derivative, a natural log of 2 would pop up. So taking the antiderivative means that we're dividing by the natural log of 2 instead. And then I suppose putting a plus c there would be good. So we could go through and simplify those fractions, but it's not a huge deal. I think we're good. Yeah, those are, yeah, it is kind of bothering me. 21/8 x to the 4/3 plus 3 x to the 1/2, and then yeah, minus, oh, we could even throw this in the numerator to save space. All right, that looks a little cleaner. Not a big deal. All right, I think we're good though. Those are a couple antiderivatives. Yeah. All right, here we're gonna be able to flex our antiderivative skills to make a function. And maybe it would be good here. I'm gonna create a little bit of space here, I think, just so that we have enough room to write and we don't have to squeeze things too bad. Okay. I made a note here just to create the position function. That's fine. Anyways, we've got a ball thrown up. It's going up at 64 feet per second at the start. We're also standing on a platform so that as it leaves the thrower's hand, it is 96 feet above the ground. We don't have a function here. We just are giving an initial velocity and an initial position. I might go ahead and label these things. If I'm labeling an initial velocity, that would be like the velocity function evaluated at 0. Then this one would be the position function evaluated at 0. Position, we can go ahead and give that h for height because we're measuring how high this ball is up in the air. Okay. So yeah, we know a particular value of the velocity function. We know a particular value on the height function, but we don't have any, position function to work with right now. The other thing that we know is that the acceleration is a constant thing because we're doing, just free fall type motion. So the only force that's acting on this is gravity as it's, flying through the air. And so that would be contributing to acceleration. Let's go ahead and use purple. The acceleration should be negative 32 feet per second squared. So negative 32 feet per second per second. This is, yeah, feet per second. Okay. But yeah, the cool thing about the acceleration function is that it is the derivative of the velocity function. It's also the second derivative of the position function. And so we can use antiderivatives to keep building back and try to make a velocity function and try to make a height function. So if we take an antiderivative and go v of t, then we would have negative 32t. We're reversing the power rule on that part. And then we would have a plus c here. Um, as we'll see in this context, that plus c is actually going to be v of 0. So, if we wanted to solve for that plus c, we could set that equal to 0 and figure out what t value we need to do. Yeah, if we go v of 0, that means we get negative 32 times 0 plus c. So v of 0 is just c, and c is just, 64. So v of t being negative 32t plus 64 is a good way to go for the particular antiderivative that we're working for in this case. And now, it's too much purple. We're going to change to green for the position function. We're going to take another antiderivative for the position function. And in the same way, we'll go ahead and do it. We get negative 16t squared plus 64t, and then plus a c that might be there. Again, we can solve for c by putting in 0. I should not have put a derivative sign there. That was messed up. Okay. Yeah, if we throw in 0 into this height function, we'd get negative 16 times 0 squared plus 64 times 0, and then plus c. And so h of 0 ends up just being c, and h of 0 is 96. So c is equal to 96, and the height function that we get, which is the position function, is negative 16t squared plus 64t plus 96. And so, if you ever need a quick way to find, um, a parabola describing the height of some kind of falling object, you know, it's really easy to just know that this part's coming from acceleration, so that negative 16t squared, that'll be there as long as it's measured in feet per second. This part is our velocity function, the initial velocity. This part is the initial height. Um, and so, yeah, if we wanted to go through and say, when does this ball reach its maximum height, we would have to, maximize this function. And we totally can do that. We could figure out where v of t is equal to 0. It looks like, oh, hey, if we put in 2 in for t, this thing would be 0. So when does it reach the maximum height? T equals 2. What is that maximum height? We could throw in t equals 2 into this thing. When does the ball hit the ground? We could set this equal to 0 and solve and factor and all that good stuff. Everything there is just gravy. Okay. We're doing well. Let's see if we can do this one and maybe introduce 5.1 as well, and I think we'll be in a good spot. Example 6. Given the graph of f prime in figure 4 and the knowledge that f passes through the point 1, 2, sketch the graph of f. Okay, so we're looking at f prime, and I know that I've kind of thrown this kind of thing on your homework before and even on the last activity that we did. But it wouldn't hurt to take some time and think through this again. I want to go through that head and look at some of the characteristics on f of x and think about the implications for that on f. What do we see on f prime? So it looks like we reach a maximum around x equals 1. So I don't know, yeah, like f prime of 1 looks like it equals 0. It looks like x equals 1 is a max. Okay, so utilizing those pieces of information, what does that tell us about f of x? Well, oh, um, no, that's not what I want. Sorry, I misspoke. I wrote this down. X equals 1 is a maximum on that. That's something that we can interpret. But saying that f prime is equal to 0 at 1, that was totally wrong. F double prime is equal to 0. But yeah, that's not super relevant. We're trying to go the other way, not think about the second derivative. Um, so my bad. All right, let's say that we've got a maximum at x equals 1, and it looks like, that's at the point 1, 8. Let's do this. What does that mean for the antiderivative? Well, it means that this would be, one of the steepest points on the line. Steepest uh, local slope, and the slope is 8. 8 at x equals 1. Okay, so that's good. Let's go ahead. Maybe we can start drawing these things as we figure them out. I'll go ahead and do a sketch over here. So the first thing that they told us is that we're going through the point 1, 2. So let's go 1 over in the x direction and then 2 up in the y direction. Boom. That's a good spot. And the idea is at this point, we should have a slope of 8. So I might go ahead and just sketch in a little positive slope there. And that should be the steepest local slope, and things should taper off in either direction. Um, at C, all right, let's look at x equals C real quick. X equals C, we get, f prime of C is equal to 0. We also get that over there. But anyways, that means that we're going to have a flat slope at C. So horizontal, yeah, let's just call it horizontal. Horizontal slope at C. Oh, geez. Okay, that's good. And same with x equals D. So actually, so on this, yeah, we should be able to go out to C, which looks like it's over here, and then D that looks like it's out here. And we'll have flat slopes at both of those spots. Maybe I don't know where to locate those exactly right now. Um, another thing to realize is that, we have positive values. So f prime of x is positive on the interval c to d. And that means that we're going to have positive slopes going from, c to d. So positive. I guess I should make this one open interval. Sorry, I should have written open interval from C to D down here, because we do actually equal 0 at C and D. Positive slopes on the interval C to D. Okay. So yeah, we're going to have positive slopes for that entire time. If we wanted to get better estimates of what those slopes actually were, we could go over to, y values over here. So, the y, the y-intercept on this one looks like it should be about 5. So instead of having a slope of 8, when we get to this point, we should have a slope of about 5. So I would actually estimate that maybe, I don't know, maybe we cross the y-axis down here somewhere. Um, and yeah, once we get to -1, it looks like we would be at a negative slope. So when we get to C, that's where we've got our flat slope. Um, and likely on this one, we would go up until we get a flat slope on D as well. Let's make that a little bit better. Um, but yeah, if we went all the way over to -1 here, the y value is almost -4. So, expecting a slope of -4 over here wouldn't be impossible. And then we would also expect, I guess if I scroll over here a little bit, we would expect this to start coming down too after D because we've got negative y values over here. So the overall flow of this function should look something like connecting these slope lines. Um, and yeah, this sketch is not going to be exact, but it gives you the general idea of what this function would look like. So yeah, those are the kinds of things that you can do. Um, I don't exactly know how we're doing on time. Um, I'd like to let's get through this example and then we can be done. I think we'll leave the definition of like the limit definition of the definite integral for next time, but doing a couple Riemann sums will be good. Okay, so remember integrals? Remember that video that you watched at the beginning of class? If we wanted to calculate the area underneath this curve, shaded in blue, we could take a definite integral, and we're going to do that later. If we wanted to write that definite integral, we would write the integral from 0 to 1, so x equals 0 to x equals 1 of x squared. This part is called the integrand, and then times dx. You'll see why we need dx later. Um, but yeah, if you end up doing that analytically, it ends up being 1/3. So that's the true value that we're actually working for. But right now, we don't know how to do a definite integral. We haven't talked about the fundamental theorem of calculus. So the best thing that we could do is approximate the area, and we can get a feel for these things called Riemann sums by, trying this out. Um, the first one that we see here is called a right-hand Riemann sum. And we call it right hand because we're using the right hand of each of these little intervals to determine the height of our rectangle. So if we wanted to estimate the area of this curve using a sum of rectangles, we could. We would just go and we would say that this area, it's the approximate area. So we can put little wavy lines there. Um, we would add up the areas of these rectangles. So we're going, base times height for all of these. The base of all of these rectangles is just 1/4 in length. So the first one would be 1/4, and then the height of this would be 1/4 squared. Since we're using this one as our input to find this height, we're multiplying this times 1/4 squared. Um, yeah, and then we would add on the next rectangle. So 1/4 for the base and 1/2 squared for the height. Next rectangle, 1/4 for the base, 3/4 squared for the height. Oh, geez. And then the last rectangle, 1/4 for the base and 1 squared for the height. And yeah, I mean, we could continue to, do this, and what's this? 4 times 4 times 4 is 64. So this is like 1/64 plus, this will be 1/16 plus 9/16 plus 1/4, and we could, figure out what that is. Um, it should be, you know, somewhat close to 1/3. We could type that in no calculator and figure it out, maybe after we do this one as well. So there's the right-hand Riemann sum, and we could contrast that with a left-hand Riemann sum. Left-hand Riemann sum. Um, yeah, so here we would be estimating the area by adding, 4 more rectangles. Uh, Sadly enough, the first rectangle doesn't have any height at all because we're using an input of 0 to start for the height of our first rectangle. So the base of that rectangle is still 1/4, but the height is 0. So we square that. And yeah, the area of this first rectangle is 0. That's fine. The next one, 1/4, and then we're using 1/4 as the value to get the height of this rectangle. So we're squaring 1/4. 1/4 for the base, 1/2 for the height for the third rectangle, and then the fourth and final rectangle is 1/4 for the base, and then 3/4 for the height. And so you can see that there's definitely, a connection between these two. The first rectangle in this right-hand Riemann sum is actually the second rectangle in this left-hand Riemann sum, and so on and so forth. Um, and yeah, if we were gonna, calculate this area, we'd have 0 plus 1/64 plus 1/16 plus 9/16. Um, and the idea would be is that the true area should be in between these two. Um, yeah. Let's go ahead. Let's bring up the GeoGebra and actually get a value for these things. So if I wanted to go 1/64, come on, not there. 1/64 plus 1/16 plus 9/16. Um, that's the right-hand Riemann sum. Or sorry, yeah, this is the left-hand Riemann sum. Um, and the right-hand Riemann sum was just adding 1/4 onto this. So yeah, it's 41/64, but I want, yeah, okay, it's about 0.64. Does that make sense? That seems high. Am I crazy? Um, hmm. That seems high for a left-hand Riemann sum. All right, pause. I'm gonna think. Okay, I figured it out. Good grief. This is 9/64. What was I doing? Um, all right. Yeah, this thing needed to be lower than a third. All right, so this is about 0.22-ish. Um, let's go back to this to show you. Yeah, this should not be 9/16. I don't know what I was doing. There's an extra factor of 4 on the bottom there. Come on. There we go. This one also is not 9/16. This needs to be changed to 9/64. This needs to be changed to 9/64. My bad on that one. Um, so yeah, that's about 0.22. When we add in a fourth onto that, I guess we'd be adding on 0.25. So um, let's go, and that would be 47 roughly, which is okay. That's fine. Those are those are roughly on the order of 1/3 of what we were aiming for. So This is an overestimate. Obviously, we've calculated more area than we needed. Here, it's an underestimate. We've calculated less area than we needed. And the cool thing is that setting up the expectation for Monday is that when we use more rectangles, our estimates get better. So if we were to utilize 10 rectangles, we would get these. This would be our right-hand Riemann sum, and this would be our left hand. If we used 100 rectangles here, if we used 1,000 rectangles here, and like the idea is the more rectangles that you use, the more accurate of an approximation that you get. And so like we were utilizing the limit as h goes to 0 to do our derivatives, we're going to use the limit as n goes to infinity to calculate integrals. And um, yeah, that'll be cool. We'll look at the limit definition of the integral on Monday. It's going to be great. We're going to learn about sigma notation and all that good stuff. All right. I hope you have a wonderful weekend. We'll see you then.